Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on filter design. Okay, so for this video, there are actually two parts. Okay, the first part, I will discuss how can we actually design a low-pass filter using LUM element. Okay, I probably have done this video, okay, but I would just want to make this video complete. So the first task that I'm going to do is to discuss how can we actually design a low-pass filter using LUM element. The key objective of this video is to do filter transformation. What is actually filter transformation? Okay, for example, for this video, I'm going to show it to you how can we actually transform from low pass filter to high pass filter. Okay, so basically this will be the objective of this video. Okay, on my next video, I will discuss another two forms of filter transformation. Okay, the second one will be the low pass filter to band pass filter. And the last one, which is the third one, will be from low pass filter to band stop filter. Okay, but this will be the next video. This video, I mainly will be concentrate how can we actually transform low pass filter to high pass filter. This will be the part 30 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter. Okay, so this is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, if you want to have a faster response, okay, you can always ask me through the comment. Okay, before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Okay, so this is the first task that we are going to do. Okay, I'm going to show it to you how can we actually design a low pass filter using LUM element. Okay, so basically this is the example here. Okay, so we are actually tasked to design a maximum flat low pass filter, okay, with a cutoff frequency of 2 GHz, impedance of 50 ohms, and at least 15 dB insertion loss at 3 GHz. Okay, so over here you can extract, for example, the cutoff frequency of this low pass filter need to be happen at 2 GHz. We have input and output at 50 ohms, and we need to achieve at least 15 dB of attenuation when the frequency is at 3 GHz. So how can we approach? Okay, the first thing that we need to know how many order that we need in order to achieve this 15 dB of insertion loss at 3 GHz. So basically, this is the first task that we need to do. Okay, so like what you mentioned here, first we need to find the required order, okay, of this maximum flat filter so as to achieve the insertion loss 15 dB at 3 GHz. Okay, so basically this is the equation here. So basically this will be the insertion frequency. Okay, so this will be the insertion frequency. This will be the cutoff frequency. Okay, the insertion loss here I need to achieve, okay, at 3 GHz need to be at least 15 dB. So this will be 3 GHz. While the cutoff frequency will be equals to 2 GHz. So 3 over 2 will be 1.5 minus 1, and therefore I got this 0.5. Okay, so once I got this, I actually can refer to this diagram here. So basically with this diagram, you can see that I actually have calculated this will be equal to 0.5. So therefore, I will draw a red line, okay, of 0.5. Where to stop? Basically, you can see that I need to achieve 15 dB of insertion loss. So I stop around 15 dB here. So from here, you can see that this is the point here. So I need to have either n equals to 4 or n equals to 5. Okay, but I cannot accept n equals to 4. Okay, because once I actually select n equals to 4, I am definitely not able to achieve this 15 dB of insertion loss. Maybe let's say 13 or 14 dB loss at 3 GHz. So hence, for this case here, I need to choose n equals to 5. Because once I choose n equals to 5, I am pretty sure that I will be able at least to achieve better than this 15 dB of insertion loss at 3 GHz. So therefore, I will choose this n equals to 5 as is denoted over here. Next, Okay, so once I done this, I actually refer to this table here. So basically, I need to do this n equals to 5. Okay, so basically, this will be the characteristics. Okay, so the question tasks me to do a maximum flat low pass filter. So basically, you refer to this table here. So over here, you can see that this will be all the parameters. Okay, I actually rewrite these parameters here. So basically, G1 is equal to 0.618. You can see from here, G2 is 1.618. G3 will be equal to 2. And you can see that they actually repeat. So therefore, I can conclude that G1 will be equals to G5 and G2 will be equals to G4. So therefore, over here, what I need to do is I just need to do G1, G2, and G3 will be good enough. Okay, because they are symmetric. So therefore, from here you can see that G4 is equals to G2 and G5 will be equals to G1. So hence, I just need to do the first three. Okay, will be enough. Okay, so let's continue. Okay, so basically, this will be how does a low pass filter look like, okay, for a lump element. Okay, so basically, this will be a lump element. Okay, you probably can see that the values here. So now I'm going to show it to you how can we actually achieve all this value here. So basically, in short, you just imagine that this will be a low pass filter structure here. So this is the G term that I actually obtained earlier on. Okay, so basically, this will be the general formula. Okay, I believe I have discussed this, but like what I mentioned earlier on, okay, I just want to make this discussion complete. So I redesigned this again, this low pass filter again. So how to get this C1 here? So this C1 you can see from here, this will be equal to C1. This will be C1 over R naught WC. So basically you can see from here. So C1 is equal to G1, which is 0.618. Okay, so R naught will be 50 ohms. Okay, WC, which is 2 pi FC. The cutoff frequency is at 2 gigahertz. So from here, if you punch your calculator, you should be able to achieve this 0.984 picofarad as C1 over here. Okay, as for L2, you will be using this set of formula. So L2, you use this set of formula. Okay, so basically, R0 will be 50 ohm. L2 will be G2, which is 1.618. Okay, divided by this 2 pi f, again, the cutoff frequency will be 2 gigahertz. And if you punch this in your calculator, okay, I think most likely you will be able to achieve this number, okay, which is 6.438 nanohenry. Okay, so this will be the L2 value. Okay, so this will be the L2 value. They are symmetric. Okay, C1 and C5, they are symmetric. So next, I'm going to design the C3 value here. So C3 value I actually obtained from here. So this will be C3 R naught KWC here. So basically, this will be C3 will be equals to 2, okay, because G2 G3 will be equals to 2 here. So R0 is 50. So this will be 2 pi FC, which is 2 gigahertz. So from here, okay, you can actually calculate that C3 is actually equals to 3.183 picofarad, which is denoted over here. So basically over here, okay, I have successfully designed a low pass filter using lump element. Okay, so I think this concept is pretty straightforward. Okay, and then you can easily design this low pass filter. Okay, so let's move on. Okay, so basically this is what I want to discuss for this video here is basically on the filter transformation here. So basically you can see that this filter transformation, okay, basically is available in most of the book over here. Okay, but this is without any impedance scale. Okay, so what I want to do is this is actually with impedance scale. Okay, so basically this will be with impedance scale. Okay, so basically you can see that I actually have add in the R0. Okay, so those without impedance scale, there is no R0. Okay, so once I actually include the impedance R0 inside, this means that this is with impedance scale. Okay, so as I mentioned earlier on this video, I'm going to show it to you how can we actually transform this low pass to high pass filter. Okay, so basically this will be the objective. Okay, so this is what I have calculated earlier on based on a low pass filter. Okay, as I mentioned, basically this will be easily designed, okay, based on a quick discussion earlier on. So basically next, what I'm going to do is how can we actually transform the low pass filter to high pass filter. Okay, for low pass filter to high pass filter, you can see from this diagram here, okay, basically inductor need to become a capacitor in order to be achieve high pass. And whatever that is capacitor, I need to change it into inductor, okay, in order to achieve the behavior of high pass filter. So from here, you can see that, okay, so this will be a capacitor. I need to change to inductor. This will be an inductor. I need to change to a capacitor. Okay, so this will be a capacitor. I need to change to an inductor. Okay, so basically this will be mirror image. Okay, so with this, I'm actually ready to design the high pass filter. So how can we actually design the high pass filter? Okay, this I just put it, this two here, I just make it smaller and put it here in order to make the discussion complete. Okay, so basically this will be all the G term, okay, that I mentioned earlier on. Okay, so basically nothing will be changed. Okay, so this will be the transformation from low pass to high pass. Okay, so basically from here, the first thing that I'm going to do is L1. Okay, so basically high pass filter is an inductor. Okay, low pass filter is a capacitor. So how to calculate? We'll be using this formula here. So my L1 will be R0 WCC1. Okay, because this will be the first term here. So how can we actually got the number? R0 is 50. Okay, so this WC is equals to 2 pi F. Okay, F will be the cutoff frequency which is at 2 gigahertz. This C1 will be equals to G1, which will be equals to 0.618. Okay, so from here, I can actually calculate that my L1, okay, will be equals to 6.438 nanohenry. Okay, so basically this is how we actually transform, okay, from low pass filter to high pass filter, from C to L, and basically I have shown it to you how can we actually obtain the L value, okay, by this formula, okay, in order to get this 6.438 nanohenry. So next, we are ready to do this C2 here. So basically, this will be a high pass filter. Okay, so capacitor at high pass filter. Okay, at low pass filter will be an inductor basically from here. So I know that I need to use this formula. Okay, so from here you can see that I actually copy this formula over here. Okay, so what's next is basically 1 over, okay, R0 is equals to 50. Again, this WC is equals to 2 pi F. Okay, the cutoff frequency is 2 gigahertz. L2 will be equals to G2, so therefore will be 1.618 over here. So again, if you punch your calculator, you should be able to get this 0.984 picofarad. So next, I'm ready to design my L3. Okay, so basically again, this will be for my high pass filter will be an inductor, okay, which means over here, and my low pass filter will be a capacitor. So basically, I make use of this formula here. Okay, everything will be still the same. Okay, R0 will be equals to 50. Okay, this WC is equals to 2 pi F, cutoff frequency of 2 gigahertz. Okay, this C3 now will be equals to G3, which is equals to 2. So from here, I actually calculate that my L3 is 1.989 nanohenry. Okay, so if you still remember, I told you that they are actually symmetric. So C2 will be equals to C4, L1 will be equals to L5. So basically with this, I have actually designed my low pass filter. And then from my low pass filter, I actually convert them into high pass filter. Okay, so basically this is what I call this as a filter transformation from low pass filter to high pass filter. Okay, so basically whatever I calculate, okay, I just put it over here in order to make the discussion complete. So basically this will be a high pass filter. Okay, so with this, I like to end my discussion. Okay, please help this channel, okay, by like this video. Okay, when more of you guys actually like this video will have a higher chances to reach up a larger audience. So guys, help me press the like button now. If you have learned something from this channel, please consider to subscribe and turn on your notification bell. Once again, guys, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.